According to Article 250.189 of the National Electrical Code, NEC, all electrically conductive material that is not part of a circuit path, that is, non-current carrying metal parts, must be grounded. In the situation of a motor mounted on a carriage, the carriage is electrically conductive and is not part of the circuit path. Therefore, it must be grounded. There are two options for grounding the carriage. Firstly, install a separate equipment grounding conductor EG from the carriage to the beam. This can be done using a flexible grounding strap or conduit. Secondly, if the motor frame is securely bolted to the carriage and the motor cable has an EGC, the grounding path through the motor may be sufficient. The recommended approach is to use a separate EGC from the carriage to the beam. This provides a dedicated grounding path that is independent of the motor cable. This is especially important if the motor is ever removed or replaced. The EGC should be sized in accordance with Article 250.122 of the NEC. All connections should be made using approved fittings and techniques. The beam should be properly grounded to ensure a low resistance path to ground. Providing a separate EGC from the carriage to the beam is recommended for proper grounding. While the motor cable ground may be sufficient in some cases, the use of a separate EGC ensures a reliable and code-compliant grounding path. The purpose of grounding is to provide a low impedance path for fault current to return to the source, thereby facilitating the operation of overcurrent protective devices like circuit breakers or fuses. This helps to minimize the risk of electrical shock and fire hazards. The equipment grounding conductor EG plays a critical role in this process. It connects the non-current carrying metal parts of electrical equipment to the grounding system. Proper sizing of the EGC is crucial to ensure that it can safely carry the fault current. Article 250.122 of the NEC provides guidance on sizing the EGC based on the rating of the overcurrent protective device protecting the circuit. The EGC must be large enough to handle the available fault current without overheating or causing excessive voltage drop. The type of EGC used, such as wire, cable, or conduit, can also affect its ampacity and suitability for the application. When installing the EGC, it's important to use approved fittings and techniques to ensure a reliable connection. Improper connections can create high resistance points, which can impede the flow of fault current and compromise the effectiveness of the grounding system. All connections should be made in accordance with the NEC and manufacturer's instructions. The grounding system as a whole should be designed to provide a low impedance path to ground. This includes the grounding electrode system, which consists of grounding electrodes such as ground rods, ground plates, or metal water pipes that are buried in the earth. The grounding electrode system should be properly sized and installed to ensure that it can effectively dissipate fault current into the earth. Regular inspection and testing of the grounding system are essential to verify its integrity and effectiveness. Ground resistance testing can be used to measure the resistance of the grounding electrode system. Continuity testing can be used to verify the continuity of the EGC and other grounding connections. Any deficiencies found during inspection or testing should be promptly corrected to maintain the safety and reliability of the electrical system. In addition to the NEC requirements, local codes and regulations may also apply to grounding systems. It's important to consult with a qualified electrical inspector or engineer to ensure compliance with all applicable requirements. Understanding and implementing proper grounding techniques is essential for electrical safety. By following the guidelines outlined in the NEC and other applicable standards, you can help to protect people and property from the hazards of electrical shock and fire. Remember that electrical work can be dangerous, and it's always best to consult with a qualified electrician if you have any questions or concerns. The NEC is a comprehensive set of standards that covers a wide range of electrical safety topics, including grounding, wiring, overcurrent protection, and equipment installation. It's updated every 3 years to reflect the latest advancements in electrical technology and best practices. Staying up to date with the NEC is essential for anyone involved in the design, installation, or maintenance of electrical systems. The NEC is not law, but it is widely adopted by state and local jurisdictions as the basis for their electrical codes. Compliance with the NEC is often required by law, and it's essential for ensuring the safety and reliability of electrical systems. The NEC is organized into chapters, articles, and sections, each covering a specific topic. Article 250, which deals with grounding and bonding, is one of the most important articles in the NEC. It provides detailed requirements for grounding electrode systems, equipment grounding conductors, and bonding jumpers. Other relevant articles include Article 300, which covers wiring methods, Article 400, which covers flexible cords and cables, and Article 430, which covers motors and motor circuits. The NEC also includes tables and examples that provide guidance on sizing conductors, selecting overcurrent protective devices, and performing other calculations. These tables and examples can be very helpful for understanding and applying the NEC requirements. The NEC is available in both print and electronic formats. The electronic version is often preferred because it allows for easy searching and cross-referencing. The NEC is also available through online subscription services. Continuing education is essential for staying up to date with the NEC and other electrical codes and standards. Many organizations offer courses and seminars on electrical safety and code compliance. These courses can help electricians, engineers, and other professionals to stay informed about the latest changes in the NEC and best practices for electrical safety. Certification is another way to demonstrate competence in electrical work. Many organizations offer certification programs for electricians, engineers, and other electrical professionals. Certification can enhance career opportunities and demonstrate a commitment to professional development. Grounding and bonding are essential for electrical safety. By following the requirements of the NEC and other applicable standards, you can help to protect people and property from the hazards of electrical shock and fire. Remember that electrical work can be dangerous, and it's always best to consult with a qualified electrician if you have any questions or concerns. Always ensure that all electrical work is performed by qualified and licensed professionals. Improper electrical work can lead to serious injuries, property damage, and even death. It is crucial to prioritize safety and adhere to all applicable codes and regulations. Before commencing any electrical work, it is essential to conduct a thorough risk assessment to identify potential hazards and implement appropriate safety measures. This includes wearing appropriate personal protective equipment such as safety glasses, gloves, and insulated footwear. Additionally, it is important to use properly insulated tools and equipment and to ensure that all circuits are de-energized before working on them. Lockout-tagout procedures should be followed to prevent accidental energization of circuits. Regular safety meetings and training sessions can help to reinforce safety practices and ensure that all personnel are aware of the potential hazards associated with electrical work. A culture of safety should be promoted throughout the organization, with everyone taking responsibility for their own safety and the safety of others. In addition to following established safety procedures, it is important to be aware of the specific hazards associated with different types of electrical work. For example, working on high-voltage equipment requires specialized training and precautions. Similarly, working in wet or damp environments can increase the risk of electric shock. It is crucial to understand the potential hazards and to take appropriate steps to mitigate them. Electrical safety is not just a matter of following rules and regulations. It is also a matter of using good judgment and common sense. If something does not seem right, it is important to stop and investigate before proceeding. It is always better to be safe than sorry when it comes to electricity. By prioritizing safety and adhering to best practices, it is possible to minimize the risks associated with electrical work and to create a safe working environment for everyone. Remember that electrical safety is everyone's responsibility. We will now elaborate more on grounding and bonding in electrical systems. Grounding refers to connecting electrical equipment and systems to the earth. This provides a path for fault current to flow back to the source, which helps to trip over current protection devices and prevent electrical shock hazards. Bonding refers to connecting together all metal parts of an electrical system that are not intended to carry current. This creates a low impedance path for fault current to flow, which helps to minimize voltage differences between different metal parts and reduce the risk of electrical shock. The grounding electrode system is the primary means of connecting an electrical system to the earth. It typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal water pipes that are buried in the earth. The grounding electrode system should be properly sized and installed to ensure that it can effectively dissipate fault current into the earth. The equipment grounding conductor, EC, is used to connect the non-current carrying metal parts of electrical equipment to the grounding system. The EGC provides a low impedance path for fault current to flow back to the source, which helps to trip over current protection devices and prevent electrical shock hazards. Bonding jumpers are used to connect together different metal parts of an electrical system that are not intended to carry current. Bonding jumpers help to create a low impedance path for fault current to flow, which minimizes voltage differences between different metal parts and reduces the risk of electrical shock. The size of the grounding and bonding conductors should be based on the size of the overcurrent protection device protecting the circuit. The NEC provides tables that specify the minimum size of grounding and bonding conductors based on the ampere rating of the overcurrent protection device. All grounding and bonding connections should be made using approved connectors and fittings. Improper connections can create high resistance points, which can impede the flow of fault current and compromise the effectiveness of the grounding system. Ground fault circuit interrupters, GFCIs, are devices that are designed to protect people from electrical shock hazards. GFCIs monitor the current flowing in a circuit and trip the circuit if they detect a ground fault. Ground faults occur when current flows through an unintended path to ground, such as through a person's body. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas, where there is a high risk of electrical shock. Arc fault circuit interrupters of size are devices that are designed to protect against fires caused by arc faults. Arc faults are unintentional electrical discharges that can occur when electrical insulation is damaged or worn. SIs monitor the current flowing in a circuit and trip the circuit if they detect an arc fault. SIs are required in many locations, such as bedrooms and living rooms, where there is a high risk of fire. Surge protective devices, SPDs, are devices that are designed to protect electrical equipment from voltage surges. Voltage surges are temporary increases in voltage that can damage or destroy sensitive electronic equipment. SPD divert the surge current away from the equipment and safely to ground. SPD are recommended for all electrical systems, especially those that serve sensitive electronic equipment. Regular inspection and testing of grounding and bonding systems is essential to ensure their effectiveness. Ground resistance testing can be used to measure the resistance of the grounding electrode system. Continuity testing can be used to verify the continuity of grounding and bonding conductors. Any deficiencies found during inspection or testing should be promptly corrected to maintain the safety and reliability of the electrical system.